the indeterminacy of the trust, okay? I think actually the trust you have learned before in your structural mechanics or in other modules. And then some of that actually you have learned before, and then I will quickly go through it. For those part that you haven't learned before, I will spend a little bit more time on that. Okay, so we will talk about some common types of the trusts, classification of the coplanar trusses, method of joints, zero force members, method of sections, compound trust, compact trust, and interspace trust. So actually there are some common types of the trusts. For the trust, actually, I think you know about that. Actually, it is form of so-called the slender member. Usually they are joined together at the end points. And at the end points, usually they are connected by the bolting or by welding. And then usually the ends of the member will be connected at the gusset plate. So you can see that this one we call it as a gusset plate. And then they will be bolt or they will be welded together. And then usually the line of action, you can see the line of action, they will point to the same point here. That means actually there will not be any movement within the member. So the truss member are just axial force member. That means they just have either compression or tension force within the members. And then the truss actually is very common structures to support the roof and then to support the bridges. Where we use the truss, basically if you have a very large opening, say for example for the exhibition hall, then instead of using a beam,
上堂一路做緊聽日嘅功課。你沖完涼啦？你唔想過嚟同爸爸一齊上堂啊？咪過嚟一齊上堂。你食埋先。
OK。
一上堂，一齊上堂啦！你又上堂啊？爸爸學緊嘢啊。
Okay, we will mute the others, okay? Let me check. Okay, for others, please mute your mic, okay? When you are attending the class, okay? Okay, thanks. Okay, 嗱。OK， 好似都瞄咗。OK, it doesn't matter. OK, then we can go on. OK, now then usually we can have a truss structures like that, and then usually we will have a very large opening below. Usually this can be a very large span. For example, for the industrial building or for the exhibition center, sometimes you really need very large opening. Just like in the hall for singing con, and then also for the exhibition hall, we don't want a column to appear in between. So for large span, actually, we will use the truss to support the roof, something like that. Like for an airplane, right here, if like in a HECO, if they want to fix an airplane, then the airplane will have a very large span, and then we don't want a column between. So we will use a very large truss to support the roof structures, okay? So this is very common structures. And then for the roof, usually we will put the truss at the different distance. So this is the first truss right here. And then I will put my second truss some distance away. And then in between, I will put the pooling. And then the pooling actually will apply the load. I mean, the roof will apply the load to the pooling. And then the loads will transfer from the floor to the pooling. Pooling, you can imagine that it is a beam which connect the truss together. And then the loading from the roof, just like a one-way slab system, it will transmit to the pooling. And then from the pooling, the loads will transmit to the truss. And then the loading will add at the joints of the truss. And then finally, through the actions of the members, the loads will transfer to the column and then down to the foundations, okay? So that's how the loading will transfer from the roof and then from the pooling, and then from the pooling, it will add the loads to the truss, and then finally will transfer to the ground. So when you have your analysis, always when you have your truss, the loads will just add on the joint. Because actually all the joint will connect it to this kind of purlins. The purlins you can imagine actually it is a type of the beam, okay? The loads will transfer from the roof or from the slab and then go to the purlins. After going to the purlins, the loads will be transmitted to the joint of the truss, that means here, and then through the members, and then usually, I mean, finally will be transmitted to the columns, okay? So when we have our analysis, all the loads will just apply at the joint of the truss structures. And then according to the arrangement of the members, and then we will have different names for the truss. They can be scissors, they can be Howell, and then they can be fan. It doesn't matter. They just give different names to the truss. And then for the bridge trusses, it is very similar. The loads actually will transmit from the deck. That means the vehicle will transmit, I mean, passing the bridge, and then it will transmit the loads to the deck first. And then just like a one-way slab system, again, the loads will transmit to the stranger below, because this one just like a one-way slab, and then the loads transfer to the stranger here. And then from the stranger, it will transmit to the bottom beam, or we can call the floor beam here. And then from the floor beam, the loads will transmit to the joint of the truss. So again, you can see that actually the loads from the deck will transmit to the stranger. And then from the stranger, it will transmit to the floor beam. And then from the floor beam, it will be transmit to the joint of the truss. So that's why when you have your analysis, you always apply the loads at the joint, and then you will analyze what is the force in the member. And then you will design what is the size of the member finally, okay? We never apply the load in the member here. No. We just apply the loads at the joint. Okay, so this is the assumption. We always apply the loads at the joint of the structures. And then for the bridge trusses, again, depends on the arrangement of the member. We can have different name, Parker, Howell, Warren, etc. Okay, but don't worry about that. It's just the name for the structures. Okay. And then basically there are two assumptions. First of all the members are joined together by smooth hinges. That means if you have a truss here, they are actually joined together. We assume that there are hinges in between. If I have this assumption, that means all the members are axial force member. or here I actually stay here. Axial force member means that within the member there only be tension or compression. And then there is no shear, and then no bending moment. We just assume that there will be either tension or compression force within the member. Okay, no bending moment and then no shear force within the member. And then all the loads will, or all loadings are applied at the joints. That means all the loads will apply at the joint only. Actually, I have just mentioned the loads will be transmitted to the pulling and then apply at the joint for the truss, for the roof. For the bridge, actually will from the decking and then to the stranger and then to the floor beam and then finally apply at the joint of the truss. So all the forces will just apply the joint. Okay, so these two are the basic assumption for truss member. Okay, and then we will have the so-called the axial force member within the truss. Okay. Now you have actually learned that in your structural mechanics, but just a revision for you right here. And then for the planar truss, or we can call it the coplanar truss, 即係一個平面嘅 truss 啊。Then we will have some classification for that. We can have three types. First of all, we can have simple truss, and then we have compound truss, and then we can have complex truss. But for your information, basically, a triangle is a very rigid system. And then to prevent actually the collapse of the structures, actually your framework of the truss should be formed by triangle. So you can see that in your crane, tower crane that collapsed in an incident before, actually the structure itself is formed by triangles, okay? Because triangle itself is a very stable structures and then very rigid structures. So you can see that for this frame, originally it is a rectangular shape. Without the bracing, you can see that without this bracing, then the whole frame will collapse, okay? So if you want to make it to be stable, you should add these additional member. We can call that the bracing, and then to form triangles. Okay, triangle is a very stable unit. And then if your truss is formed by many triangles, then the truss will be stable. So if a truss actually is formed by triangles, then we can call that they are actually a simple truss. So you can see that for the first unit right here, you add two more members and then to form additional triangle, and then you add two more and then add two more. So this kind of thing we can call or classify it as a simple truss. Or actually you can see that you have this basic unit first, and then you add two additional member here, and then you add this additional member here to form different kind of triangle. So we call that a simple truss if formed in this way, okay? So what you have learned in your structural mechanics actually is the simple truss. And then compound truss actually is formed by connecting two or more simple truss together. We just connect the simple truss together, then we call that as a compound truss, just like a compound beam. We connect the beam together by a hinge. If we connect the simple truss together, then actually we will call that as compound truss, okay? And then we can connect them by a hinge, or we can connect them by a link. I will show you later. And why we need to have the compound truss? Because sometimes it is cheaper to construct a lighter compound truss than a heavier simple truss, okay? we can connect the simple trust together to provide a longer span or other uses, and usually it will cheaper in this way than making a very large simple trust. And then for the compound trust, there are actually 3 types. For the first type, as I mentioned, they will just connect by common joins and then a link, or we can call it a bar. Okay, this is so-called the type 1. For the type 2, actually, 2 simple trusts are connected by 3 bars. For the type 3, actually, it is well, large trust, and then some of the member actually formed by the trust. We call that the secondary trusts. Now I show you in the figure, then you will understand it quickly. Now you can see that for the first one here, this is the type 1. For this one, you can see that the simple trusts are actually connected by a hinge and then by a member here. Then this one, we call it the type 1. For type 2, the simple trusts are actually connected by 3 members. So we call that this is the type 2. And then for type 3, you can see that some of the members actually becomes a simple trust. We call that this one as the secondary simple trusts. So instead of 1 member, actually it is replaced. This is the simple member, okay? And then this is actually replaced by the secondary simple trust here. Then for this type of the trust, we can call it the type 3 compound trust, okay? And then if a trust it does not belong to so-called the simple trust or compound trust, we will call that as a complex trust, okay? And then just similar to the beams and then to the frame, we can count the determinacy of the trust, okay? Again, we need to count the number of unknowns and the number of equilibrium equations for a trust. But for the unknown, actually, the total number of unknown is composed of 2 parts. The first part is actually the force in the bars of the truss. And then the second part is actually the number of unknown external support reactions, okay? So this actually, the first one depends on the number of truss member. And then the second one is actually depends on your support conditions. And then when you add them together, it becomes the total number of unknowns. And then remember, the support reactions should not be concurrent or parallel. Otherwise, it will be unstable. So we can take a look. For here, actually, the number of unknown is B plus R. Here, the number of unknown is also B plus R. So B is the number of unknown here, and then R is the number of support reactions. For each of the joint, this one should be summation Fx is equal to 0. This one is summation Fy is equal to 0. Sorry about that. This is the display error for the PowerPoint. So actually, for each joint, if you still remember, we use the method of joint. For each joint, we can write down 2 equations, 2 equilibrium equations. So you can see that this is the total number of unknown. This is the number of bars. And then this is the number of support reaction. And then for each joint, we can write down 2 equilibrium equations. So if B plus R is equal to 2J, then it is a statically determinant truss, just like what we learned before for beam or for frame structures. If B plus R, that means the unknown is more than the equilibrium equations, then we call that it is statically indeterminate truss. And again, if B plus R is smaller than 2J, that means the number of equilibrium equations is more than the number of unknown. Again, it will collapse for the truss. And then just like before, even though a truss is statically determinate or statically indeterminate, the truss can still be unstable. And then the instability will be depends on the support condition. And then one more thing is that we will consider the internal stability for truss structure. So for the support condition, just like the beam and then the frame before, if we have parallel or concurrent, so this one is the concurrent support condition. And then the one on the right-hand side is the parallel support condition. Then both of the truss will be unstable because of the improper support conditions. So for this case, we call that the external stability. Or if the truss is not stable because of the arrangement of the support condition, then we can call that it is externally unstable, because they are either concurrent or parallel. And then another thing we call that is internal stability. The stability can be also affected by the internal arrangement of the member. Now you can see that for this one, actually this truss is a stable truss. I mean, if you count the number, it is a determinant truss, okay? However, you can see that this one actually is rigid because this is a triangle. This one is also rigid because this is a triangle. This one is also rigid because of a triangle. However, you can see that the one in between here, actually it is not formed by triangle. So as a rigid body, this part, we can think that it is a rigid body. That means it does not deform. This part is also a rigid body. So if I have a force applied at the corner at the D, what do you think about the structures? Do you think it will move or it does not move? Actually, if you apply the load right there, the structures will rotate a little bit. Then it will have something like that. Then this one will also rotate a little bit. If you apply a load like this. Then actually this one is a rigid body. That means it does not move. This one does not move as well. But when you apply the load, actually for the whole structures, because the middle part actually can deform, then actually we can call that this one is actually moved due to the rotation of the rigid body. And then we call that this structure is internally unstable because it forms a so-called a critical form. So actually this one is a critical form. Now, of course, for sure, you can check it by so-called inspection. Inspection means that you can take a look to the truss, whether any part of the truss is not formed by triangle. Then actually they can deform and then make your truss to become unstable, okay? Or actually you can still use the so-called equilibrium equations. You can write down all the equilibrium equations and then solve for all the unknowns. And then in that sense, actually, you will find that the results are inconsistent, saying that you use the first equations, you will solve for certain value of a member force, and then you use another equation, you will use a different answer for the same member, because actually your truss is not stable, okay? But for that, actually, you will spend a lot of time and then you will find that the answer is not consistent. And then by inspection, actually you can check whether your truss is stable or not, because some part of the truss actually is not formed by triangle. And then for instability, it can be also due to the bar concurrent. You can see that all the 3 bars which connect to the smaller truss inside, they are actually concurrent right here. You can think of actually the support forces on the member are actually concurrent. And actually will make the truss to become unstable internally. So this is another example of internal instability. So for here, actually, as I mentioned, if you can have inspections, then you can tell whether the truss will be stable or unstable internally. Or if you don't know whether it is stable or unstable, actually you can solve the 2J simultaneous equation for the joints and then for all the unknowns. So the results can be received by solving all the simultaneous equation and then all the unknowns. And then you will find that the results are inconsistent. Then in that sense, actually prove that the structure is unstable. So if you cannot tell whether the truss is internally stable or not, then the way actually you can solve is to solve all the unknowns by all the equilibrium equations. Then if the results are inconsistent, that means your truss actually are unstable, okay? Okay, right now, again, we can count the number of members, count the number of joints, and then to see whether our joint is a statically determinant truss or indeterminate truss, stable or not, okay? So right here, I can count for you, and then we can take a look. So first of all, we need to count the number of unknowns, B plus R. So number of bars we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there are 19 number of bars, okay? And then for the support reaction, there are 1, 2. So sorry, this one should be this one should not be a support reaction. So there should be 3 support reaction. So for the number of unknown, you can see that it is 22, right? Then for each joint, if you still remember, we can write down 2 equilibrium equations. Summation fx is equal to 0 and summation fy is equal to 0. So we can count number of joints here. Here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there are 11 joints, okay? So the number of equilibrium equation is equal to 2 times 11, because for each joint I can write down 2 equilibrium equations. So there are totally 22 numbers of equilibrium equations, and then I have 22 unknowns. So you can see that the number of unknowns is equal to the number of equilibrium equations. So finally, I can tell that it is a determinant truss here, statically determinant truss. And then, well, externally, the support reaction are not concurrent, and then they are not parallel. So it is externally stable. Internally, you can see that all of them are formed by triangle. So actually it is also internally stable, okay? So for this one, we can say that it is a stable truss. Okay? Do you agree? Okay, then for this one here, we can do the same again. You can try to count number of members. We can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I will just use 10 here. And this one 11, 12, 13, 14, 15. Okay, so the number of members is equal to 15. And then for the support reaction, both of them are pin support. So actually it is equal to 4, okay? So the total number of unknown is equal to 19. Okay? Okay, then I will try to count the hinge here. It is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are totally 9 joints. So J is equal to 9. So the number of equilibrium equation is equal to 2 times 9. This is 18. So, well, you can see that the number of unknowns is 19 and the number of equilibrium equation is 18, right? So the degree of indeterminacy is equal to 1. And then you can see that the support conditions are not parallel and then they are not concurrent. So they are externally stable. And then internally, you can see that all of them are formed by triangle. So it is internally stable, okay? And then for this one, well, you can count the number of bars. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have number of bars is equal to 9. And then support reaction here, you have 2 unknowns. Here you have 1 unknowns. So R is equal to 3. So the total unknown is equal to 12. Okay. And then the number of hinge here, you have 1, 2, 3, 4, 5, 6. So you have 6 join. And then each join, 6 join. And then each join you can have 2 equilibrium equations. So totally there are 12 equilibrium equations. You have 12 equation and then you have 12 unknown, right? So actually it is a determinant truss. And then you can see that externally, the support conditions are not concurrent and then they are not parallel. And then internally, you can see that all the bars are not concurrent. So again, this is a stable truss. Okay. And it is determinant. Okay, now this one actually of course you can count. But before you can count, you can see internally, do you think it is stable or unstable? You can see part of the structures here. Actually, there's no triangle, right? So actually the truss will deform inside because within this part, actually, they are not formed by triangle. Then actually you will have internally instability, okay? Of course, if you count the number, you will also find that it is unstable. But by inspection already, you can see that internally it is not stable, okay? Internally, it is unstable, okay? Okay, so we can take a look. So actually the answer is in the notes, so don't worry about that. So you can see that already it states that it is a statically determinant truss, and then by inspection, the truss is internally stable and externally also stable. And for this one, again, this one is the statically indeterminate truss to the degree of indeterminacy equal to 1. And then the truss is both internally and externally stable. For this one, again, the number of equilibrium equation is equal to the number of unknowns. And then by inspection, it is both externally and internally stable. And then for this one, if you count the number, B is equal to 12, and then the reaction is equal to 3, while the number of join is equal to 8. So actually it is 15 here for the unknown, and then the equilibrium equation is equal to 16. Well, actually the number of equilibrium equation is more than the number of unknowns. So actually the structure is unstable. And actually you can observe that because the internal part, not every single part is formed by triangle. So actually it is internally unstable, okay? And then for the method of join, actually, I think you have already learned in your structural mechanics. So I will just quickly go through it because you have learned that before. Just like an example here for a triangular truss, if you want to solve all the members, you can do it by considering the joints one by one. Because for each joint, actually, you can write down 2 equilibrium equations. You can write down summation fx is equal to 0, and then summation fy is equal to 0. So for each joint, you can write down 2 equations to solve for the unknowns. So to start off the analysis, first of all, you have to find a joint with 2 unknowns only. Well, you can start at the joint B, because at the joint B right here, if you consider the equilibrium, right here is actually the free body diagram at the joint B. 500 Newton is the externally applied force at the joint B. And then BA and then the BC, both of them actually, you don't know about the answer. So both of them are the unknowns. Now usually, a good practice is that when we don't know the answer, usually we will assume the force is a tension force. That means it is go away from the joint. And then if you know that actually it is a compression, then actually you can assume that the force points towards the joint. If it is point away from the joint, you can see that this one is point away from the joint. Then it is actually a tension force. And then if we push towards the joint, actually it is a compression force. And then if you use the equilibrium equation, you will find that if it is a positive answer, it means that your assumed direction is correct. So positive just means that your assumed direction of the force is correct. So for the case of FBA, if you got a positive answer in your equilibrium equation, that means the answer is tension. However, for the FBC, because at the first you assume that it is a compression force. If in the equilibrium equation you got a positive answer, that means your answer is correct. That means the force is in compression. Okay, so don't mix it up. Don't ask me a question. Hey, Simon, if my equilibrium equation is positive, then my member is positive. I mean, is compression or tension? That depends on your assumption. Right now, at the first, you assume that FBA is a tension force. If you got a positive answer, that means your assumption is correct. Then it is a tension force. And then for FBC, you assume that at the first, you assume that it is a compression force. So if you use the equilibrium equation and then you got a positive answer, that means you assume the direction is correct. So it is a compression force. So positive can be tension or can be compression. You know what I mean? Depends on your assumption. So a good practice is that you always assume that it is tension. So positive means tension. You can assume in this way. OK 嗱，即係小心啲啊，唔好問我究竟你個答案正咧係代表拉力定係壓力啊？係好 depend on 你本身 assume 你個 force 係 tension 定 compression 嘅。總言之，你嗰個 equilibrium equation 如果係正嘅話咧，個答案係正嘅話，即係話你 assume 嗰個 direction 係啱咁解。OK。So I would just mention about that, and then right here, a positive answer indicates that the sense is correct. And then a negative answer indicates that the sense should be reversed only, okay? So in the equilibrium equations, don't always think that positive is tension, negative is compression. It depends whether you assume that it is tension or compression at the first. Okay. So right here we get an example for you. We apply the force 3kN, 2kN, and 3kN at different joints. And then we can use the method of section, method of joints to solve for all the answer. Now remember, for the method of joint, we can just have two equations. So we always start with a joint with two unknowns only. If a joint with more than two unknowns, actually we cannot solve for that because we just have two equilibrium equations, okay? So do you think you can start at the joint F? No, because you have four unknowns, okay? Can you start at the joint G? No, because you have three unknowns in this case, okay? So if you know the support reaction here, you can start at the joint A, or you can start at the joint D. Then use the equilibrium equation, you can find these two members' forces. Then the next one, you will consider the joint G here. You can find the other two. And afterward, you can consider joint B here. You can find the other two. And afterward, you can consider the joint D here. You can find these two. And afterward, you can consider joint E. You can find the other two. And then finally, you can consider joint C. You can find the remaining member. Okay. So when you consider the method of joint, start with a joint with two unknowns only. If you have more than two unknowns, then you cannot solve for that. So right here, say for example, you can consider the joint A. Then you have the unknown FAG right there and FAB as shown. That's a good practice. If you don't know whether it is tension or compression, you always assume that it is tension. That means it's point away from the joint, okay? Then positive answer means that it is tension. Negative answer mentions that it is compression, okay? But it doesn't matter, actually. You can assume that it is tension or compression, but just remember, positive means your assumed direction is correct. Again, this question mark is actually summation. Sorry, it's pointing upward as positive. Pointing upward as positive. This one pointing to the right is positive. And then this is 4 pointing upward as a 4, so it is a positive force. FAG, you have a component pointing downward. So FAG times sine 30 degrees is actually the vertical component of the force. Then you can get FAG is equal to 8 kN because it points towards the joint, so it is a compression force. And then you have FAB here. This is the force here, FAB, and then times, minus 8 cosine 30 degree, because FAG, you just find that it is equal to 8. So the horizontal component will be in the negative x direction. So FAB minus 8 times cosine 30 degree is equal to 0. And then you can find that FAB is equal to 6.928 kN. And then the next one, you can consider the joint G. And then for this one, you can have the x-axis, and then you can have the y-axis. And then again, you can consider the force at the joint G. So here is a error in showing pointing upward as positive. And then this one is also summation, pointing to the right as a positive. So you have FGB, and then you times sine 60 degree. And then this one is actually in the y direction. So right here it is in the y direction. This is the component of the force. And then you have 3 cosine 30 degree. Again, this is component of the force. So from this one, you can get FGB is equal to 3 kN. And then afterward, you can consider the Fx is, the summation Fx is equal to 0. So you have 8 kN here, and then you have 3 times sine 30 degree. It is again the force, the horizontal component of these 3 kN. And then you have 3 cosine 60 degree because you have this component. And then finally, you need to consider this FGF. Then you can find the values. FGF is equal to 5 kN. Okay? So just consider the equilibrium at the joint, then you can find for the unknown answer. And then again, finally, you can consider the joint B, again, the pointing upward as positive. Summation. This one, summation, pointing to the right as positive. Okay, this one also you consider the horizontal component of the force and then the vertical component of the force is equal to 0, then you can find for the unknowns. Okay, so this one I think you can get that because it is not difficult. Just consider the horizontal and then the vertical force component is equal to 0. And then from that, actually, for every truss, actually we can locate some, we call that the zero force member. That means there's no force inside the member. If we can find that, actually you can simplify your truss and then make your calculation faster. Then actually there are two cases for the zero force member. Say for the first case is that when there are two members, they are connected together, and then there's no additional force applied at the joint, then we call that it is a zero force member. So right here, you can see that this for the first member here and the second member here, they connected at the joint C. And then there's no external force applied at the joint C. So both of these two members are zero force member. Now, if I draw the free body of the joint here, I have the force FBC here. And then vertically, I have the joint force FCD here. If I consider the joint at the C here, okay? Then I need to know summation Fx is equal to 0, right? Then negative FBC is the only force in the x direction. So this one must be 0, right? And then I also have the summation Fy is equal to 0. Then I have negative FCD must be equal to 0. Okay? So if I have two joints, they are connected together. I mean, two beams or two members, they are connected to a member, to a joint here. Then if there's no external force applied at the joint, then both of the member actually are zero force member. Okay? They do not need to be in 90 degrees. Say for example here, if there's a hinge here, it will be like that. Then say for example, I have a joint here, and then the members join together, not in a 90 degree. So you can write down a member force here. I can call that as a FA. And then right here, I can call this the FB. Say this is angle theta. Then you can see that for the summation Fx is equal to 0, or summation Fy is equal to 0, then FB times sine theta negative must be equal to 0, right? Because I can consider this vertical component and then this horizontal force component of the force FB. FB sine theta is the vertical component, must be equal to 0. So we know that this one sine theta is not 0, so FB must be equal to 0. Right. If FB is equal to 0, then we consider summation FA is equal to 0. So negative FA is equal to 0. So FA is also equal to 0. So the conclusion is that whenever there are two members, they join together, no matter this theta is 90 degrees or not, then both of the members are zero force member. They have no force inside the member. OK？ 即係雖然之兩條 member connect 埋一齊，冇一個力咧篤喺個 join 度嘅話咧，咁嗰兩條 member 都係 zero force member， 冇力嘅。So both of them are zero force member. Okay. And then you can see that at the joint A, I also have two members there joining together, right? So for this case, these two are also zero force member. Okay. 個 truss 咁多 member， 其實只係呢個三角形受力嘅啫。 其他都冇力嘅。Okay. All the forces actually just transmit by these 3 members. Other members are actually zero force member. They're useless in this case. 你加好多條鐵上去都冇用嘅，其實得啲三角形有用嘅啫嘛，即係啱啱呢個三角形，其餘嗰啲冇力嘅。I can tell immediately if I can consider the zero force member. Okay. So for the case 2, for the zero force member, if there are 3 members, they are connected together, while 2 are in the same direction, then the 3rd member must be a zero force member. 即係有3條黐埋一齊，其中2條咧同一直線嘅話咧，第3條一定係0。And then for this case, they do not need to be in 90 degrees. They can be in any angle. Okay. And this one must be a zero force member. Okay. You can solve it in equilibrium. But don't worry about the equilibrium first. If you take a look to this truss, can you locate any zero force member? So you can take a look to the joint at the D here. They are connected by 3 members, right? CD and then DE are in the same line. Then this DF is not on the same line. So this DF is a zero force member. Do you agree? 總言之，3條黐埋一齊，其中2條喺同一直線嘅，第3條咧就係 zero force member。You know what I mean? I just find a joint with 3 members. They are connected together. And then 2 of them are actually in the same direction. The 3rd one is the zero force member. So in this case, we can consider joint F here. GF and then the FE are in the same direction. Then this member is a zero force member. Okay. That means there is no force within the member. Agree? Of course, we can use the equilibrium to check that they are zero force or not. But I can tell that actually FCF must be a zero force member. So for here, you can tell which one are zero force member. 你可唔可以講到俾我聽邊個係 zero force？ 得2款嘅啫，其實呢度你都可以馬上講到啊。So here I just mark all the zero force member. Okay. Now for the joint D, they are connected by these 2 members, and then there's no force applied to joint D. So it is the case 1 zero force member. And then for the joint H here, you can see that there are 3 members, they are joining together, and then 2 of them are actually in the same line. the first one must be a zero force member. So this one is case number 2. And then for here, you can see that for the joint E here, you can take a look to the equilibrium equation. This is a P here. And then horizontally, it is a zero force member. Then, of course, horizontally, this must be also be equal to 0 to be in equilibrium. Then the force applied the FCE. So FCE must be equal to P if you consider the joint E here, right? And then just like for the joint E, you can consider the joint G here. So you have a support reaction here. And then you have a force within the member FGF. And then this is a support reaction, okay? And then vertically, actually there's a force at the FAG. But the summation Fy must be equal to 0. So FAG must be a zero force member, right? Do you agree?即係佢一定要平衡㗎嘛。喺 X 嘅方向加埋一定係要等於0，喺 Y 方向加埋都一定要等於0。如果你喺E 個方向睇嘅話，你右邊呢條一定係 zero force member， 咁左邊你呢條都一定要係 zero force member。如果唔係，你 summation fx 咪唔係等於0咯。OK， 睇個 joint G 亦都係，你 summation fy 一定要等於0啊嘛，咁所以 vertical 嗰條 member 一定要係0先得。You agree？ Okay. It doesn't matter. Go home and then take a look if you don't understand. For here, of course, sorry for the question mark. Actually, it is going upward and then summation. This one again, this is summation. So I just show you if you use equilibrium equation, you can still get those equations. I mean, those forces are equal to 0. So here is again summation. This one is going up as a positive. This one is again goes up. It's a positive. Why? So actually, you can consider equilibrium equations and then to show that those zero force member have no forces inside the member. And then again, we will have the so-called method of sections. So this one is also the thing that you have learned before. So for here, actually, for the method of joint, we will consider joint one by one, and then use equilibrium equation to find all the member forces. However, actually, sometimes we do not need to know every single member force. Say, for example, I just want to know the member force of BC, GC, and GF, these 3 answers. Okay, I just want to know these 3. Then I do not need to solve them one by one. Instead, I can cut a free body at these 3 members. And then by considering equilibrium, then I can find for the answer for these 3 members. So you can see from here, actually, you will cut at the section for BC, for CG, and then for GF. So you can cut it here. Okay, and then once you cut, you can see that the force inside the member FBC, FGC, and FGF are exposed. Okay. Then I can use 3 equilibrium equations to find for these 3 answers. I can use summation fx is equal to 0. Summation fy is equal to 0, and then summation of moment is equal to 0 to find for free answer. So I can use, for each part, I can use summation fx is equal to 0. Summation fy is equal to 0. And then summation of moment is equal to 0. And then to find for these three answers. Okay? 三條 equation, 三個人弄. Okay? And for this one, actually, you can consider the left-hand side. This one is left-hand side. Or you can consider the right-hand side to find for the answer. 你求其考慮一邊都得嘅。But if you have a choice to choose left-hand side or right-hand side, will you choose left-hand side or will you choose right-hand side? 有得俾你揀，你揀左邊定揀右邊？ Don't forget, if you choose the right-hand side, you will need to solve for the unknown support reactions. Okay. So one of you have already answered to choose the left-hand side. Yes, it is more efficient to choose the left-hand side to solve for the answer. Then you can see that the forces are actually connected at the joint C here, and then connected at the joint G here. So to be quick to find all the answer, you can use summation of moment at the joint C is equal to 0. Then you can solve for the FGF. Because it is the only unknown if you use summation of moment about the joint C, because both of the force actually points towards the joint C. So it will not appear in the equilibrium equation. And then the only unknown is FGF, okay? And then the next one is that you can use summation of moment at the joint G. Then in this case, actually both the unknown FGC and FGF are pointing to the joint G. Then from that you can find the force FBC here. And then finally, FGC, you can use summation Fy is equal to 0. Because just FGC has the vertical component. Then you can find for FGC here. Okay. That means you use free equilibrium equation to find for free answers. Okay, so I just give you an example and then you can take a look. Say, for example, you want to find the force in member GJ and in the CO. Then actually you can see that you can cut the members here. And then you have the CO here. If you cut here, you have the GJ here. Then you use the equilibrium equations, then you can find for the unknown of CO and then for the members GJ. Then again, sorry about that, the question mark is actually summation of moment. Then on the right-hand side, you can see that if you cut the section, you can see all the forces are here. Then, because actually you want to find the values of GJ, then you will take moment about I, because you can eliminate FKJ and FGH right here. Because both of them are actually point to the joint I. So you will not create any moment about the joint I. Only FGJ will be the only unknown here. And then for this one, your FGJ, you can decompose it into the vertical component and then the horizontal component. And then if you consider the moment about I, so only the vertical component will create the moment. So you have FGJ times sine 30 degree times the moment arm equal to 2 meter. So it is actually a clockwise moment. So it is a negative value. We assume that counterclockwise is positive. And then another force is 1,200 and then times the moment arm 1.155. Then from this equilibrium, you can find for the answer is equal to 1,386 Newton in compression. Okay? Do you know what I mean? And then on the left-hand side, again, you will consider taking moment at the A is equal to 0. So summation of moment about A, and then counterclockwise is positive. So you will eliminate FOP and the FCD because both of them are actually passed through the point A here. And then the only unknown is FCO. So you have FCO times the moment arm is equal to 2. And then you have 1,200 times the moment arm equal to 1.155 meter. And then from this equation, you can find the FGC is equal to 693 Newton, okay? This one is actually the one you have learned in your structural mechanics. I think you should be able to handle it, okay? You may take a look again when you're at home. Here I give you one more example. You can see that I want to find the force GF and then the GD. So I will cut the section here and then to explode the force. So I want to find GF and then I want to find GD. So right here, I can take the moment at the D. If I take the moment at D, then actually the only unknown I have is FGF. And then this force, actually, I can extend the so-called line of action. And then I can assume that actually my FGF is acting at the point O here. Then for my force, actually, I can decompose it into two components. The vertical component and then the horizontal component. Then just the vertical component will create the moment. So sine 36.6 and then times the moment arm equal to 6 meter is the negative moment. And this 7 kN is the support reaction times the moment arm 3 is another moment. So the FGF is equal to 7.83 kN. And then for the next one is actually we can consider taking the moment at the point O here. And then GF and then the CD are actually pointing to the point O. So the created moment is equal to 0. And then we can consider FGD is applied at the joint D. And then of course you can decompose it to two components. So it is FGD times the 6. Because actually the moment arm is equal to 6 meter. And then it will create the counterclockwise moment, so it is a positive value. Don't forget at the same time, we have 2 kN pointing downward and 77 kN pointing upward. If we take moment about the point O, then actually we just have the force and then times the moment arm. Okay. Now, for this one, you have actually learned before. I think you can handle it, actually. Don't worry too much. You can go home and then try to take a look. You need to see whether you can write down the equilibrium equations. If you cannot do that, just come to me again, and then I can show you how to do that. For the compound truss, as I mentioned, actually just connect the simple truss together. So we will use the method of section and method of joint to solve for the answer. Like for here, if I have a compound truss like that, then what will I do? First of all, I will use method of section. Just like here, I will cut it as a section in the dotted line here. So I will cut it here. And then I will expose the force, FHG, FJC, and FBC here. And then I will take moment about the joint. C, actually this one is C, summation F, summation of moment C is equal to 0. Then the only unknown is FHG, because FHG have the moment arm equal to 4 times sine 60 degrees. So this force, and then times the moment arm here. And then because I'm taking moment about the C here, then 5 and then times 4 is the moment arm. And then the other one is 4 times 2 is the applied moment. Then FHG can be calculated as equal to 3.46. So you have this 3.46 here. And then these two are the unknown forces. If you take a look to the example again, here it is a force, and then here there are two unknowns here. Okay, so after finding this force, these two unknowns are just exposed and then placed in the free body diagram. So here, these two are actually the forces connected. Right there is these two. Okay. But don't worry, you just use method of joint. You consider joint A, then you can solve these two. You consider the joint H, then you can solve these two. You consider joint I, then you can solve these two. You consider joint B, then you can solve these two. You consider joint J, then you can solve this one. So you just solve it one by one, then you can find for the answer. You know what I mean? Just consider joint one by one, and then each time you can solve for two unknowns. And then finally, you can solve for all of them. And then finally, not finally, is the next one is the complex truss. The complex truss is a little bit more tricky when you try to solve it. I will show you as an example here. Now this is a complex truss. Now you can see that this truss is a bit difficult. Why I say that? Because if you take a look to the joint, there are 2 or 3 unknowns here. You can see that for here, there are 3 unknowns. For here, there are 3 unknowns. For here, there are more than 3. There are many unknowns in one of the joint, okay? So you cannot solve it easily by using method of joint, okay? And then again, if you cut at the member, you try to use method of section, then there are also more than 3 unknowns at each time when you cut at a section. So you cannot simply use what you have learned, just like method of join and method of section, to solve all the answer. Now, of course, you can list all the unknowns and then list all the equilibrium equations by solving n equations, n unknowns by n equilibrium equations. You can solve for that, but it will be very time consuming. Like instead, we will use a so-called the superposition method to solve for that. Now, right now, we will have the so-called the complex truss. So the first thing is that I will turn a complex truss to a simple truss. So for here, you can see that I have a truss like that. I will take away this member and then add one member in horizontal direction, okay? So the first thing I need to do is to turn a complex truss to a simple truss. So you can see that I will take away the vertical member. And then I will add one horizontal member here. And then you can see that the force is still equal to 20 kN here. So the original vertical member have been taken away. And then this one is newly added. So I will change a complex truss to a simple truss like this. And then if it is a simple truss, then I can use method of join or method of section to solve for all the answer. So I can consider this join, and then I can solve for these two member. Consider this join, I can solve for these two member. And then consider this join, I can solve for these two. Consider this join, I can solve for these two. And then consider this join, I can solve for this one. And then I can solve all of the answer. Okay? Just I turn a complex truss to a simple truss first. 由一個複雜嘅或者好難嘅 truss， 我會變咗個 simple truss 先。Then I will put my original force right here at the original join here. And then the next one is that originally I have a vertical member here, but I just take it away. So right here, I need to add the force back. And then I assume the force is equal to 1 kN. Okay? But the idea is that I will write down for you. Now this is my original complex truss, okay? Now I will decompose it to two simple truss. This is the first one. Okay, I eliminate the vertical member and I add a horizontal member. And then the other one is that I will add back this internal force here, and then I assume that is equal to 1 kN. I use the method of superposition. I decompose the force into these two. Is that well, the case 1 plus case 2 is equal to the original one. Okay. This 1 is actually to simulate the internal force of the member. Now you may ask, hey, Simon, there's no horizontal member here. Then how can I do that? Because you have a horizontal member here. The case is that if this one is called the BD here, this SDB here is due to the case 1. This small dB here is due to the case 2. If the force they act together is equal to 0, that means this member does not exist, okay? So I have to make sure that the horizontal member in case 1 plus the horizontal force member in case 2 is equal to 0, so that actually this horizontal member does not exist. Agree? 嗱，我用中文講一次嘅，我哋呢個做法咧，係夾硬咧用一個叫 superposition 嘅諗法，將 case 1加 case 2咧等於 original case。大家有個印象咩叫 superposition 啦？係咪？將一個複雜嘅 case 咧變做兩個簡單嘅 case 加埋咧，我哋就叫做 superposition 啦。咁咧，因為打動嗰條 member 咧，而家嗰個力咧，我唔知係幾多嚟嘅，我掹走咗佢先。咁喺 case 1嗰度咧就冇打動嗰條 member 喺度。咁喺 case 2嗰度咧，我就將打動嗰條 member 嘅力咧，我加翻落去。咁我當咗係1先啦。好啦，我當咗係1嘅話咧，其實如果 under 呢個 condition 咧，我可以 solve 每一支 member 嘅力係幾多嘅。因為咧，我有個1喺度，我可以用咩方法 join， 我可以 solve 每一條 member 嘅力係幾多。即係話咧 ，case number 1咧，我可以 solve 晒呢個其實係 case 1嚟嘅。我可以 solve 晒每一條 member 嘅力係幾多。我可以計晒出嚟㗎，用咩 for section 就得㗎啦，或者咩 for join 就得㗎啦。呢個係 case 2。case 2咧就係淨係得上邊一個力，下面一個力嘅啫。我亦都可以用咩 for join 啦，咩 for section 啦 ，solve 晒每一條 member 嘅力有幾多。咁我就 list 晒喺後面呢個表嗰度啦。首先呢樣嘢有冇問題先？嗱 ，case 1咧就係有嗰20個 kN 嘅力，依然加喺呢度啦。咁我用咩 for join 同咩 for section 咧，每一個 member 嘅力咧我都揾晒出嚟。而 case 2咧，我就上邊加1個 kN， 下面加1個 kN。咁你問我，咦點要加1個 kN 嘅？因為而家我模仿翻呢個 vertical member 嘅力係幾多，但我唔知佢係幾多，我當咗係1先。咁如果我加咗1嘅話咧，每一條 member 我 solve 出嚟咧就會有個力，我就寫咗喺呢個表嗰度。咁但係我唔知我 internal force 嗰條 member 嘅力係咪真係1㗎嘛？係咪？我當咗係1啫。咁但係咧有一個 hint 咧就好重要啦。我呢條打橫嘅 member 咧原本係唔存在㗎嘛？係咪？呢條 member 原本係唔存在㗎。 而家咧我就特登咧係加咗落去。呢條 member 原本係唔存在嘅，即係我 original 嘅 structure 係冇呢條打橫噶嘛，係咪？原身。咁我點做咧？我 superposition 咧係將兩個 case 加埋咧，就會係我原本個 case 嚟。咁即係話咧，我呢條嘅 BD 揾出嚟嗰力咧 ，case one 嗰力咧，呢兩個加埋應該要係零嚟嘅，因為呢條 member 原身就唔存在，所以咧呢條 member 嘅力肯定係零嚟嘅，因為佢條 member 唔存在嘛，即係佢冇力啦。但係如果我係一嘅話咧，我睇翻呢個表咧，我 DB 嗰力咧係1.167嚟，而咧 case one 嘅力咧係-10嚟。咁我又要話俾你聽，其實 case one 加 case two 嘅呢支 member 咧要係零啊嘛，即係佢加埋要係零。咁 case one 咧就係話，如果個 internal force 我 assume 咗佢係1嘅話咧，咁其實個 member 嘅力得1.167啫喎，係咪？咁 case one 係-10，你加埋都唔係零啦，係咪？咁我係咪要將呢個數倍大某一個 percent 或者某個倍數先至可以令到佢係等於零？即係-10係 case one 啦，而咧1.167係我 internal force，如果係1嘅話，佢就1.167啫。佢倍大 x 倍之後咧，就會令到佢兩個加埋係零嚟嘅。咁所以咧，我 x 要倍大幾多倍咧？我將個10調過去啦，再除1.167，我就知道咧，其實咧要倍大8.5倍左右。即係咧呢度咧，佢計咗出嚟啦，大約8.567倍啦。換言之，其實呢個力唔係1嚟㗎，呢個力係8.567。如果我加落去呢個力係8.567嘅話咧，打橫呢支 member 嘅力就會係正10。咁咧頭先即係呢支啦，呢個咧係-10，正10加-10咧，正係0。咁咧呢次 member 就會變咗係0啦，得唔得啊？咁即係話咧，呢度每一條 member 咧都要乘大8.567倍咧，先至係啱喎。所以咧你就睇到呢個數咧，其實係乘咗8.567之後就會係呢個乘咗8.567，就會係呢個乘咗8.567，就會係呢個。而你真正最後嘅答案咧，就要將呢行加上呢行，就會係個答案。因為個 superposition 咧，要將譬如話呢條 member，其實呢條 member 係等於呢一條加上呢一條，就會係原本嗰條啊嘛，係咪？大家可唔可以理解我嘅意思啊？呢個係 case one 做出嚟嘅，呢個 case two 做出嚟嘅。但係 case two 做出嚟嗰個答案未啱嘅，因為咧我未係可以將嗰個DB 嗰條陣咧，或者嗰個打橫嗰個 member 加埋之後係0，因為我 assume 咗 vertical 個 member 咧係1啫嘛，係咪？但係其實咧-10要加上正10先至要係會係0嚟噶嘛，因為我一定要令到呢條 member 係0嚟嘅，因為打橫嗰條 member 原本就唔存在。咁原來咧嗰條 member 個 internal force 咧就唔係1嚟嘅，係8.567。 咁如果係8.67嘅話咧，打橫嗰條 member 咧就會變咗係正10啦。咁就會變咗一開頭嗰個-10加上呢個正10就會係0。可唔可以接受啊？OK。嗱，你可以翻去再諗下，我唔係要你一次過諗明白嘅，但係你諗一諗先，因為可能你一時間未接受到㗎嚇。OK，嗱，我會完埋佢先，咁咧後面仲有個 space trust 啫，咁就完啦。咁呢個你可以諗一諗，我下堂咧翻嚟同你再過多一次，咁你會好一啲，好嘛？OK。Then we will go for the space trust first, and then we will end the lecture today. Now, for the trust, actually, we have planar trust. That means it is a plain trust. And then we also have the space trust. For the space trust, actually, the stable form is also a triangle form, but it is in a 3D dimension. And then again, if it is unstable trust, that means the unknown is less than the equilibrium equations. If it is a determinant trust, the unknown is equal to the amount of equilibrium equations. And then for the indeterminate trust, the unknown is more than the equilibrium equations. But for the space trust, actually, we can write down for 3 equilibrium equations. Summation fx is equal to 0, summation fy is equal to 0, and summation fz is equal to 0. And then for the support, actually, we have 4 different types. Say it is connected to the short link, and then we have a roller support, and then we can have a roller constraint as a cylinder, and then have a ball and socket. So you can see that the reaction is one direction only for the first 2 cases. And then for the third case, there are 2 unknowns. And then for the ball joints, there are 3 unknowns, support reactions. And then for each member force, actually, we can have 3 components, X, Y, and Z component. To find the component, actually, we just divide by the length of the member, L. So L is the length of the member. And times the X component of the member. Then it will be, X component length of the member. So it becomes the X direction of the force component. And then the same thing is that we can find the Y component and then the Z component by dividing the total length and then times the corresponding direction. And then similar to the planar truss, we also have the zero force member. Say, for example, there are 4 member force connected together, while 3 are on the same plane, 1 is out of plane. Then that 1 out of plane will be a zero force member. And then the second case is that if we have 4 members connected together, while 2 of them are zero force member, then the remaining 2 will also be the zero force members. So here I just give you an example and then you can take a look. Over here at the joint C, there's actually 1 support reaction in the CY. And then the joint B is a slider, and then you have 2 unknowns. For the A, actually it is a ball socket, and then you have 3 unknowns, okay? So totally there are 6 unknowns. And then you can solve for the answer by consider 6 equilibrium equations. So you have summation fx is equal to 0, summation fy is equal to 0, and then summation of fz is equal to 0. And then you can have summation of moment about x, y, and z is equal to 0. Then you can solve for the 6 unknowns for the support reactions. And then you can consider the join one by one. First of all, you can consider the join at the B. Then you have the support reaction at the right here. You have already solved for 4 and then 2 here. And then you have 3 member forces. And then you can consider summation fx is equal to 0, summation fy is equal to 0, and then summation fz is equal to 0 to find for all the 3 answers. Now you can take a look at one by one later. I just would like to give you the idea, and then you can check for the answer by yourself. And afterward, you can consider join A. Again, you have already solved for the support reactions, and then you have other 3 forces as the unknown. And then again, you can consider 3 equilibrium equations, summation fx is equal to 0, summation fy and summation fz is equal to 0. Then you can solve for the next 3 unknowns. And then, well, because actually for the same join, 2 of them are actually shear force member, and the one out of the plane will be also the shear force member. And then for the last one here, you can see that the 5 forces are connected together, while 4 of them are shear force member, and the final one must be shear force member. Now for these several things, you can take a look afterward, and then I don't want to go into detail here. It is a long lecture today, so I think I will stop here, and then you can take a look at home. Okay, so come to me if you have questions next time. Okay, so see you guys next week, and then have a good weekend. Okay. OK， 今日好長啦，咁知道大家好攰啦，咁我哋下個禮拜如果你有問題可以再問，好嘛 ？OK， 好，拜拜。